In this video, we will discuss how to solve stoichiometry problems involving gases. Now, you've probably done a lot of these because at STP, the volume of a gas can be determined with the conversion factor that 1 mole of that gas will be 22.4 liters. So, let's see where that 22.4 liters comes from. In example 1, I have said use PV equals nRT to solve for the volume of 1 mole of gas at STP. Well, PV equals nRT. If we're at STP, that means standard temperature and pressure, and that means the ATMs equals 1.0, and that means that the temperature equals 273 Kelvin. So I can plug in some of those right now, 1.0 ATMs. We're going to solve for volume. We have 1 mole. And R is 0.0821 ATMs times liters divided by moles times Kelvin. And the temperature is 273 Kelvin. And so when I solve this out, my volume is actually 22.4 liters. And so that's where that number comes from. So before this set of notes, if you've used 22.4 liters, you are using something that comes from the ideal gas law. The reason why this is useful to know is in an example like number 2, where we are given, we have quicklime, calcium oxide, and it's produced from the decomposition of calcium carbonate. We want to calculate the volume of CO2 at STP. I would always underline or box if you see at STP if we started with 152 grams of calcium carbonate. So basically, in this problem, I want to go from calcium carbonate, 152 grams, to carbon dioxide. Okay, and I'm going to just do that using a mole bridge. So first things first, 152 grams of CaCO3. I'm going to get that to moles, and I have my periodic table in front of me. So I'm going to go to grams of CaCO3 to 1 mole of CaCO. Whoa, I don't know what I was writing there. And that molar mass is 100.09. And then now that I'm at moles, I can mole bridge, which that mole bridge is 1-to-1, 1 mole of CaCO3 to 1 mole of CO2. And I could stop right now. And if I stopped, I would have some moles of CO2, and then I could plug it into PV equals nRT. Because I'm at STP, I know temperature. I would have just figured out the moles. I'm at STP, so the pressure would be 1, and so I could solve for the volume. But what's nice about STP is I can actually save myself some time, and I could just say, well, 1 mole of CO2 equals 22.4 liters at STP, and so that'll be 34.0 liters of CO2. Easier math to do it all in one step. The reason we need to talk about gas stoichiometry is what do you do if you're not at STP? And the answer is nothing different. So we have a sample of methane gas here. It has a volume of 2.8 liters, 25 degrees Celsius, which is 298 Kelvin, and a pressure of 1.65 atmospheres. And we're going to mix it with oxygen gas, which has 35 liters, 31 degrees Celsius, which is 304 Kelvin, and 1.25 atmospheres. The mixture is going to be ignited to form carbon dioxide and water. So let's look at this reaction. This is just going to be a combustion reaction. And then to get this balanced, what I could do is put a 2 here and a 2 here. Okay. And what we want to know is the volume of CO2 that's produced at not STP, but at 2.5 atmospheres and a temperature of 125 degrees Celsius, which is 398 Kelvin. So hopefully, here's what I see, is I'm given a value of CH4 and I'm given a value of O2, and then I need to convert one of those to CO2. So since I don't know which one to convert to, this is a limiting reagent problem. So the first step I'm going to do is find the limiting, and that's going to be get moles first. There's lots of ways to get moles, but in this unit, when I'm given the liters, the temperature, and the pressure, that needs to be PV equals nRT when I'm given that information. Okay, so let's look at this. The pressure of CH4 times the volume equals the moles of CH4 RT. Then the pressure of O2 times the volume equals the moles of O2 RT. And I'm going to get moles, and I'll solve that out. And then I'm going to divide by coefficient. Okay, so I need to plug in some things here. The pressure of CH4 is 1.64 atms. The volume is 2.80 liters. The moles of CH4 is what I'm trying to solve for. R is 0.0821 atms times liters divided by moles times Kelvin. And then the temperature is 298 Kelvin. And so when I math that out, the moles of CH4 is 0.189. The coefficient for CH4 is 0.189, so I'll do that. Or is 1, excuse me. It is 1. I mathed that too quickly. The coefficient is 1, and so when I divide by the coefficient, I get 0.189. This was moles of CH4. I need to do O2 now. I'm going to make this just a tad bit smaller. Okay, the pressure of O2 was 1.25 atms. The volume was 35 liters. That's a big volume. The moles of O2 is what we're solving for. R is 0.0821 atms times liters divided by moles times Kelvin. And then the temperature was 304 Kelvin. So when I solve for O2, I'm going to get 1.75 moles of O2. The coefficient of O2 was 2, so 1.75 divided by 2. That's going to be 0.875. So what I know is that CH4 is limiting, and O2 is excess. And so once I convert, I need to go from CH4 to CO2 because I'm ultimately trying to get the volume of CO2. And I'm going to use the mole bridge to do that. If you remember from last unit, I've got 0.189 moles of CH4, and then I've got red 0.189, and I need to use this blue one. I know the numbers are the same, but the only reason the numbers are the same is because the coefficient of CH4 was 1, and so I'll go from moles of CH4 to moles of CO2. That ratio is 1 to 1. And so I am now at 0.189 moles of CO2. And I want volume, which will be liters. And so I'm just going to plug in the information for CO2 to PV equals nRT. The pressure of CO2 was 2.5 atms. The volume is what we're solving for. The moles were 0.189 moles of CO2. R is 0.0821 atms times liters divided by moles times Kelvin. And then the temperature was 398 Kelvin. And so volume, when I solve this out, is going to be 2.47 liters. So that is probably the hardest type of problem you could see in this unit, where it's a limiting reactant gas problem. Okay, we're going to do a couple example problems and we'll see if we need to do limiting reactants or not. So in this first one here, we have ammonia, and it's going to be generated or produced by mixing hydrogen gas, which is H2, and nitrogen gas, N2. I want to know what volume of ammonia can be generated if we have 30.5 liters of hydrogen at 143 degrees Celsius and a pressure of 2.27 atmospheres, and we mix it with excess nitrogen gas. Okay, so that word excess is important, under the same conditions. So my reaction is that I'm going to take nitrogen plus hydrogen, and I'm going to get ammonia. These are all gases. Put a 3 there and a 2 there to get that balanced. And nitrogen is excess. So here's what's nice, is I just need to convert from hydrogen to ammonia. And I need to do that through a mole bridge. Remember that a mole bridge is the only way you can convert between different chemicals in a reaction. And I'm not given moles of H2, but I'm given a whole bunch of information. So I'll do P of H2, V equals N of H2, RT. The pressure of H2 is 2.27 atms. The volume is 30.5 liters, and those units are perfect for PV equals nRT. We're solving for moles of H2. R is 0.0821 atms times liters divided by moles times Kelvin. And then this 143 degrees Celsius is 416 Kelvin. And so my moles of H2, when I math that out, I get 2.03 moles. Okay, to get to NH3, I'm just going to mole bridge it over there. So 2.03 moles of H2. There's 3 moles of H2 for every 2 moles of NH3, and so I have that math is 1.35 moles of NH3. Let me remind myself what we're solving for. We are ultimately solving for what volume of ammonia, and we're actually under the same conditions, which is kind of rare for these types of problems. Usually they change up the pressure and temperature on us, but they don't. So what I can do is I can actually just copy this. I'll put this down here. This is PV equals nRT. The conditions that are the same would be not the volume, but just the pressure and the temperature. So I can plug in the moles that I got through my mole bridge. And so I'll solve for volume, and I'll just divide over 2.27 atmospheres, and I end up with 20.3 liters of NH3. Okay, so let's look at number 2. Number 2, we have HCl, and we prepare it, meaning HCl is a product, by reacting NaCl with H2SO4. And this looks to be just a double replacement reaction, and we get HCl, which in this reaction is going to be a gas. That's kind of rare, plus Na2SO4, and that'll be aqueous. And then to get this balanced, this will be 2, and this will be 2. Okay. We want to know what mass of NaCl. So we're ultimately going to need to get back there, and we want grams of that. What mass of that is required to produce enough HCl to fill 340 milliliter cylinder at a pressure of 1.5 atmospheres at 20 degrees Celsius. So 20 degrees Celsius, that is going to be 293 Kelvin. So PV equals nRT. The pressure is 1.51 atms. The volume is 340 milliliters, which milliliters is not what I can plug in here, but that's an easy conversion. That's just 0.340 liters equals the moles of HCl times R, which is 0.0821 atms times liters divided by moles times Kelvin. And then the temperature is 293 Kelvin. So when I solve for the moles of HCl, I get 0.0213 moles. And now I've got to think, how am I going to get that to grams of NaCl? And the answer is going to be just a mole bridge. And so I have 0.0213 moles of HCl. There are 2 moles of HCl for every 2 moles of NaCl. Now that I'm at moles of NaCl, I can get its molar mass, which is 58.44 grams of NaCl. And so the final answer is going to be 1.24 grams of NaCl would be required.